Today we are going to see sufficient statistics. Here we have three methods to find sufficient statistics. First is by the conditional probability. Second one is by the Neyman factorization theorem, and third one is by the exponential family. So first we are going to see the definition of sufficient statistics by the conditional probability. A statistic P of x is a sufficient statistic for parameter theta if the conditional distribution of sample x bar given the value of P of x does not depend on the parameter theta. That is, probability of capital X bar is equal to small x bar given P of x is equal to h of x, where h of x is a function of x. Here we have the second definition by the Neyman factorization theorem. Let f of x theta denotes the joint radius or PMF of a sample x bar. A statistic P of x is a sufficient statistic for theta if and only if there exists a function g of t theta and h of x such that for all sample points x bar and all parameter point theta, f of x theta is equal to g of p of x theta into h of x. F of x theta is equal to f of t theta into h of x, where t is equal to p of x and h of x is a function of x. P of theta and b of theta are function of theta, and p of x and c of x are the function of. Here we have an example where xi follows binomial n comma theta. Here we have to find sufficient statistics for theta by the Neyman factorization theorem. We will go step by step. Let x1, x2 up to xn be a random sample and xi follows binomial n comma theta. Then the PMF is P of x is equal to x is equal to NCx theta raised to x 1 minus theta raised to n minus x, where x is equal to 0, 1, 2 up to so on, and theta lies between 0 to 1, 0 else. Our third definition is by the exponential family. Let x be a random variable with PMF or PDF belonging to a class f of x theta. Theta belongs to parameter space where the regularity condition holds and given as the support S is equal to x as f of x theta greater than 0 does not depend on the parameter theta for all theta belongs to parameter space. Parameter space is an open interval on a real line. The PDF f of x theta for x belongs to S and theta belongs to parameter space such that f of x theta is equal to e to the power a of theta into b of x plus b of theta plus c of x. Now we are going to take likelihood function of PMF. So likelihood is a product of PMF. So L of x theta is equal to product of ironing 1 to up to n P of xi is equal to xi. Now here the PMF of binomial distribution is NCx theta raised to x 1 minus theta raised to n minus x. Now we are going to apply the product on the PMF. It will become product of NCx into theta raised to summation xi and 1 minus theta raised to mn minus summation xi. Now we have to compare this equation with theta into h of x bar. So here we can see this term is a function of x and theta, and here the function of theta or the parameter is not involved anywhere here. So we are going to take this term as h of x is equal to g of t of x comma theta is equal to theta raised to summation xi 1 minus theta raised to mn minus summation xn. So now we have compared this term equal to h of x is equal to product of ncx and g of t of x of theta is equal to theta raised to x 1 minus theta raised to m minus mn minus summation xn. Now here we can see the function of theta and x is this. So now the term is over theta that we are going to take as a sufficient statistics. So here sufficient for the binomial distribution, the sufficient statistics will be summation xi. So our t will be t of x will be summation xi, because this function of theta and summation xi we have got here the summation xi. Therefore, the sufficient statistic for binomial n comma theta is summation xi. So here are the steps to find sufficient statistics by the Neyman factorization